In this video, we'll be finding the molecular orbital energies for our cyclopropenium cation. And so in the previous video, we found the symmetry adapted group orbitals. And so we're going to use those in this video to find the relative energies for our p orbitals, for our pi bonds in this molecule here. So remember, this molecule in the resonance structure has this double bond here that's sort of a resonance that can go to this bond here or that bond there. But we know from quantum mechanics that, there isn't, like, we won't find this molecule right here like a third of the time or something. That double bond is sort of, shared around the 3-point ring here, or the triangle, I guess. And so we will be finding the molecular orbital energies for that, or at least the relative energies for it. All right, so we assume that the symmetry adapted group orbitals that we found last time interact and linearly combined to form the three symmetry adapted linear combinations, the SALC MOs. So we have this trial wave function here. And so remember from a couple videos ago, the trial wave function is what we use in the variational method. And so this is our trial wave function here. So we have these as our symmetry adapted group orbitals. And so where these C coefficients here are the contributions of each of these three SAGOs here, these symmetry adapted group orbitals, to our molecular orbital. So the trial wave function, if we go through sort of what I did a couple videos ago, gives us the following three secular equations. So we have these three secular equations. So the C times the H minus E times this S here, where the S is that overlap integral. And so this is our secular determinant right here. So just as a reminder, so this H, when the I and I are the same, so we have the two phi's that are the same, and so that will just be the energy of those atomic orbitals, where this is the energy of the interaction between those atomic orbitals, and this is the overlap integral between the atomic orbitals. And so our symmetry adapted group orbitals are orthonormal, meaning that the S11 equals S22 equals S33 equals 1. And so the Sij is equal to 0 when j is not equal to I. And so we end up with this this determinant right here. So we've just turned these two here to 0. And so the S11, the S22, and the S33 have just gone to 1 on each of these. So those just are subtracting the E there. And so the H12 equal H21 equals 0, meaning that the orbitals psi1 and psi2 don't interact, and so the same thing for the H13 and the H31. So we see above that we have the one-dimensional determinant, so that's the H11 minus E, and so that's why I have it kind of put into this separate box here. And since the E isn't dependent on the psi2 or psi3, we'll just call it E1. So that's our first energy here. So we have our E1 is equal to the H11 because we need this right here to be equal to 0. And so that's equal to the integral of the psi1, the Hamiltonian, and the psi1 there. And so we put in our symmetry adapted group orbitals here for each of those two psi's up there. So we can sort of multiply this 1 over the square root of 3, 1 over the square root of 3 to get 1/3. We can move that out. And then we change each of these into we do the inner product of each of these atomic orbitals here, with the phi1, then the phi2, then the phi3. And so we get each of these these integrals here, but we see that we have this one here, and this one here, and this one here, which are just the atomic orbitals. And so those are all equivalent, and we can call that alpha here. So we can just call those alpha. And then when we have it where the I is not equal to J on here, these are the interaction energies of our atomic orbitals, phi I and phi J. And so when I is not equal to J, we will just call that beta here. And so we end up getting, if we just sort of make all those substitutions, our energy 1 here is equal to 1/3 times 3 alpha plus 6 beta. And so we get this alpha plus 2 beta here. So if we do the same thing for our 2x2 determinant up there, so we have this right here, and if we have the H₃ equals H₃, and if those are not equal to 0, then the C₃ and C₃ interact to form additional SALC MOs. But if they are both equal to 0, then there's no interaction, and they will be the SALC MOs on their own, and not just these symmetry adapted group orbitals. And so if we look at one of these where I is not equal to J, and we do the integral, we multiply those here, so we have the C₃ and the C₃ here, and if we sort of make those substitutions the same as above, where we have the alpha and the beta that we substitute into here, we have this, and this all ends up equaling 0. And so that means that the C₃ and the C₃ are the SALC MOs. And so we can reduce our 2x2 determinant to two 1x1 determinants. So for the H₂ and the H₃. And since the C₁ and C₂ are degenerate orbitals, they have the same energy, and so we can give both of those the E2 energy here. And so we only have to solve for one of them because the energy will be the same for both. Because remember, this comes from our 2x2 determinant, and so that comes from our E irreducible representation, and so that tells us that there is that degeneracy there, and so those have the same energy. So if we solve for the H₂, so we put in our C₃ and our C₂ in here, and we sort of replace those with our alphas and our betas here, we end up with a 1/6 over 6 alpha minus 6 beta, which gives us alpha minus beta. And so that gives us that our energy 2, our second energy here, is equal to this alpha minus beta. So both alpha and beta are negative values because we're always talking about negative energies here, because so if you remember, like the potential is, so if we have the potential like this, it looks something like this. And so we always have this below 0, this negative energy when we're talking about bonding here. So that means that alpha plus 2 beta is essentially minus alpha minus 2 beta. And so that's actually lower than alpha, while our alpha minus beta is higher than alpha because it's alpha minus a minus, and so it ends up being plus. And so the alpha plus 2 beta, as I said, is lower than the alpha minus beta. Recall that alpha was the energy of our atomic orbitals, so that was the substitution we made up here, where we said that when I equals J, that these are just the atomic orbitals right here. And so those are the atomic orbitals, so the alpha. And then recall that the molecular orbitals with energy lower than the atomic orbitals are the bonding orbitals, while molecular orbitals higher in energy than the atomic orbitals are the non-bonding or anti-bonding orbitals. So we therefore have one energy level, namely the energy 1, that is a bonding molecular orbital, and two degenerate energies, the E2 energies, that are anti-bonding molecular orbitals. So remember, we were looking at the p orbitals on our positively charged molecule. And so these three p orbitals here, but we only have 2 electrons that are sort of being shared amongst these, generating that double bond character. So we therefore are down 1 electron, meaning that we only have 2 electrons in these 3 orbitals. So we therefore have this as our molecular orbital diagram. So these atomic orbitals are all the same energy. I just drew it like this because I couldn't sort of draw in 3 dimensions here. But we have our E molecular orbitals up there, and our A2 molecular orbital down here, and then our 2 electrons, which go into this bonding orbital. So remember, we're talking about pi bonds here. Then we have these 2 anti-bonding orbitals up here, which are higher in energy than our atomic orbitals. That was the alpha minus beta going on right there. So this ends up being a bonding character right here. And so what we actually know just from experiments is that this structure here with that's the cation, so it's missing an electron, is actually more stable than if it is the neutral molecule. That's because if it's neutral, then we add an electron up here, which makes it slightly anti-bonding and sort of weakens that double bond on it. Whereas if we have that electron missing, then this double bond character is stronger, and it actually stabilizes this molecule. But anyway, so like I said, we were looking for those relative energies here. If we wanted to find the actual energies, we would probably use like a computer program to calculate that stuff for us, to actually solve all these different integrals that we have right here. So what we were doing was essentially just saying that we know these atomic orbitals are this alpha, that the interactions give us this beta right here. And so we can find the relative energies using this. But if we wanted the sort of actual energies, we would probably use some kind of computer program. But for just building like a molecular orbital energy diagram like this, we can just sort of know what the relative energies are for it. I'll be looking at more examples in the next few videos, kind of going through this same process again with some different kinds of molecules, but the process is relatively the same, although in future videos we will also be looking at where there is sort of interaction between the 2 different orbitals, which makes it the calculations a little bit different. So we won't be able to have this, we won't have this right here, and so we'll actually have interaction between the 2 orbitals. But anyway, I hope you found this video helpful, and I will see you in the next one.